So now I'd like to show you an RTD that has a more realistic electrostatic potential. So here's a simulation run in RTD NEGF with a RTD that has a realistic doping profile where there's a non-doped spacer of roughly 50 nanometers that keeps dopants away from the central RTD, which is 555 nanometers. And we're ramping the voltage from 0 to 1 in 51 bias points. And for this particular simulation, we have turned off the relaxation in the reservoirs. So now, as we crank up this voltage here, you see that there is a resonance forming in the emitter. So let me zoom into this energy range a little bit cleaner so you can see it more clearly. So there's a triangular well that's forming right here. And any triangular well like this will bind a state. That doesn't mean it needs to be strongly bound. Any potential modification, variation that is of negative shape will bind a wave function, or will bind a state, just like what we've seen with on top of barrier resonances. There were actually resonances above the single barrier. Now you see there's a resonance really weakly bound at a small bias, and then it's getting pulled in more and more into the center, right? So let me zoom that in. So here's this energy range. So it just sort of shows up first, just weakly bound. So here. And now it's starting to move more and more into this well. Okay? And as it moves more and more into this well, it really sees a really strong barrier here, right? This is 30 nanometers roughly, right? This is virtually impossible to tunnel through. And here you see it's off-resonantly coupled to the collector. So effectively it sees a very strong barrier. So it's really weakly coupled to the left and the right. That means it's kind of almost like a truly bound state. So it's getting really sharply bound, and we'll see that in the energy resonance. And meanwhile, we're starting to pull the central resonance here past this resonance in the emitter. Okay? So let me zoom out again and zoom in on a different energy scale like this. So let me go back. So here we're starting to couple to a state that actually starts to sit here, but it's not well identified in the simulator because it's too broad. It shows up a little bit late here, there. There's actually a second state that wasn't identified properly in this version of the tool yet. But it's there, and it's coupled to it, and then we pass the resonance through these states. So what we have here is a space of resonance versus energy versus voltage, where here's the central resonance, C1 in the middle. It's being pulled down almost linearly. Here's the central resonance, C2. It's pulled down almost linearly. And then we have coupling to an emitter-bound state, E1 and E2. And as this line should have extended here further. As this E2 is coupled to C1, we start to conduct. And as C1 couples to E1, this is also the peak current. And eventually, once the central resonance goes under the sea of electrons here, we would expect it to turn off. But in this case, it will actually turn off once the supply function in the emitter, which is determined by the emitter bound state, will turn off. So the resulting current versus voltage profile looks like this. So you have two peaks. This is associated with a coupling to the second emitter bound state. This is associated with a coupling to the first emitter bound state. And this peak here is stronger than this peak because the resonance here is much broader than the resonance here. And the proof for that is we look at the resonance energy width versus energy plot. And here we see the central resonance C1 being weakly dependent on energy. Here is the resonance E2 in the emitter. It's actually broader than the central resonance. And here we see the emitter resonance E1 getting narrower and narrower over 1, 2, 3, 4, 5, 5.5 orders of magnitude getting narrower, which ultimately then results in a current voltage characteristic that has two peaks, where the central resonance has probed states E1 and E2. Okay? All right.